Okay, I have your exams. I have to post the answer key. The scores are in, but the grades are muted, so I have to unmute them. And then you'll be up to date, except Chapter 14 top hat problems I have to put in. Chapter 15 top hat problems are due on Monday, because today we have one more topic in Chapter 15 to talk about, and then we'll move to Chapter 17, 18, whatever it is after spectroscopy. And I'll take your homework problems or your take-home quiz problems after class when I hand out the exams. Okay, so any questions about the ether stuff, the ether chapters? Okay, there's one more topic that we have to talk about with ethers, and that's this scenario. Let's say that I had, bless you, I had this molecule. So I've got an alkyl halide and an alcohol in the same molecule, and what I'd like to do is I'd like to add magnesium to this to make the Grignard. And then I'd like to take that molecule and react it with CO2 so that I could make that carboxylic acid. So that's what I'd like to do. And the question is, if I add magnesium to this bromide, am I going to be able to make the Grignard and then react it with CO2? So what do we think? No, because of the OH group. Kevin? Okay, let's be a little more specific in our terms. So if I try and make the Grignard, I'm going to have my minus with my MgBr plus, correct? So what's going to happen? The OH gets deprotonated by the C minus. So that's true. That's exactly what's going to happen. But here's what we have to think about. Whenever we do these reactions on paper, we just think we have a single molecule, right? We don't. We've got millions and billions of molecules. So even if this could stretch over and grab the H, which it probably could, then it would deprotonate it and it would kill the Grignard. But even if it can't, there's another one of those molecules, and maybe it hasn't even been turned into the Grignard, so that the O minus could come down and deprotonate it. But either way, I'm going to kill my Grignard, and I'm never going to have a Grignard to react with CO2. And so this happens a lot more than what we're doing right now, because we're just doing molecules with one functional group, which is easy. When you have more than one functional group, you have to think, okay, if I try and do this to this side of the molecule, will that react with the other one? Will it react with the other functional group? And so this is a case where I can't do this reaction. This will not work. So what I have to do is I have to what would be called, I have to protect the OH. And so I have to put the OH into a form that will not react with the Grignard, but then after I'm done with my reaction, I need to get my OH back. And so this is where we have what are called silyl ethers. So silyl ether is one method of protecting an OH group against reactions of acid or base. And so what would I do? Well, what I would do is I would take my OH group and I would react it with something like trimethyl silyl chloride. And this is abbreviated TMS and then Cl. So trimethyl silyl chloride. For those of you who are saying, TMS, where have I heard that before?
Isn't that a solvent that we use sometimes?
Not quite a solvent, but where have you heard of it before? In lab. Tetramethylsilane, another TMS, is what we use to reference 0 in the NMR. So this is trimethyl silyl chloride. And this silicon-chlorine bond is going to act like the chlorine-sulfur bond in a tosyl chloride. So when I react the alcohol with the TMS chloride, it's going to generate HCl, and I'm going to end up attaching the silicon directly to the oxygen. And so if I wanted to, I could just add the rest of the molecule there. Now that group then, that silyl ether, it's not going to react. So it will not react with acid or base, won't react with oxidizers or reducing reagents. And so it's going to basically protect the OH from further reaction. And so now what I could do is now I could add my magnesium metal. I could make my Grignard. The Grignard would stay intact. And then I could add my CO2 to make my final molecule. So the silyl ethers is one of the beginning ethers, or one of the beginning groups that we can use to protect alcohols. Josh?
How would you reduce the silyl ether back to an OH without messing up the...
I'm going to get there. Because we need to have a way to take it off. And so I'll get there in a moment. Okay, so that won't react. I can do the rest of the reaction. Now, how do we get it off? Anybody know how we get it off? Just seeing if anybody read that part of the chapter ahead of time.
Would you use NADH?
No. It really isn't going to be, it's not a substitution reaction per se. What we actually use is we can use sodium fluoride or potassium fluoride. Because that's what it says in the book, right?
Yes.
So that's good. At least I remember these things. So a silicon-fluorine bond turns out to be one of the stronger covalent bonds that we can have. So the fluorine will basically strip the silicon off of the oxygen. And so we can use fluoride then just simply to take off the, to break down the silyl ether back to the alcohol. And that fluoride is pretty specific. If there's silicon in the molecule that can be removed from the oxygen, it will be. So that isn't going to mess up anything else in the molecule. Okay. So that's probably the simplest of the protecting groups for alcohol. It's going to be sodium fluoride and water. So I'm going to end up making the alkoxide, and the alkoxide is a stronger base than water, so it's just going to pull the H off water. This would be what we would call a deprotection then. So we have protection and deprotection steps. And we'll talk a little bit more about some of these for different functional groups later on as well. There's some good ones. There's also other functional groups you can protect OH groups with. There's a mom group, and you can turn them into like benzyl. Well, you can always turn an alcohol into an ester to sort of protect it. But there's the methoxy, the mom group, and then there's also, I think, a benzyl group that you can use. But they're not quite as simple as just simply using the silicon. So I'll just give you an example. At one point in the 70s, 80s, particularly during the oil embargo days of the mid-70s, when you had like even odd gas days, you couldn't fill up your car except on an even or an odd day. I sort of remember those days. The thought was, can we replace crude oil? And one of the thoughts was, well, let's replace crude oil with sugar. So if we can, grow sugar or sugar cane, we can replace all of our plastics and stuff with that. And I don't know, it kind of went on for a while, but there are a lot of drugs where you take a sugar molecule and you attach the potent end of the drug to it so that the sugar can get into the cell and drag the whatever that drug molecule is so it gets inside the cell. If you're going to do synthesis with sugars, you have 5 OH groups. And you have to differentiate between those 5 OH groups in order to react one and not the others. And so people who do a lot of synthesis with these sort of like glucose molecules or other sugars, they end up half the time, they spend about half their time protecting and deprotecting. They're not even changing the molecule. They're just protecting this one so they can react that one, and then deprotecting it so they can react the other end of the molecule. So they spend an inordinate amount of time in protection and deprotection schemes. So it is important because in real life we don't work with molecules that have one functional group. They always have at least 2 to 15 or 20. And so we have to make sure that we know which group's going to react. So this is protection and deprotection of an alcohol with a silyl ether. And that was going to be the last part of chapter, whatever it is, 15 that needed to be gone over. So fluoride will take the silicon off, and then the silyl chloride, like the tosyl chloride, will react with the oxygen and put the group on. Right. So that's going to end the ether discussion.
Will the team SCL favor one over the other?
Well, that's what you're trying to do. Is you're trying to favor whatever you're protecting. You're trying to favor one over the other. I don't know necessarily that it'll favor. It may favor a CH2OH, or may not favor a CH2OH, depending on all these others. We'll talk about this again, because there is a way to protect 2 OHs that are cis, but they're not trans. And so when you have in the sugar 2 OHs that are cis, you can easily protect those and then react to the ones that are trans to those 2 groups. So that's part of this. You have to be very specific in terms of trying to find something that will do that. And then you have to make sure that your protecting group doesn't come off during the reaction. It's got to stay on and then you have to control it getting off. Okay. All right, so we'll talk more about this. We'll talk more about protection and protection when we get to ketones and aldehydes. But we're a ways away from there. Bless you. Free radical reactions. Let's see if I can go the entire period without saying this was the first reaction we would have started with last semester had the book been organized better. Well, I just blew that. So I don't know why it's one of my pet peeves, but it kind of changes our flow a little bit. But we're actually in a better position, I think, to understand this right now. So what is a free radical reaction? And what I'm going to do is I'm going to start with the reactions. The first few parts of chapters 17, 18, after the spectroscopy chapters, is talking about bond dissociation energies and other things. I'm just going to jump right into the reaction. So here's my reaction. I'm going to take methane and I'm going to react it with Br2 or Cl2. I'm going to react it with a halogen. Now, I got two other choices. I've got iodine, I2, that's too slow. I2 isn't as reactive enough. And fluorine explodes when it comes in contact with hydrocarbons because it's too reactive. So we're going to stick to bromine and chlorine. And so this is kind of a double substitution reaction. When the methane, the CH bond of methane reacts with the halogen, I'm going to end up substituting the halogen for the hydrogen in the methane and then substituting hydrogen for the halogen in Br2. So I'm going to end up forming the alkyl halide and the HBr. And I'm not concerned too much about the HBr. I am concerned about making the halide. Okay. So this is the overall reaction. This can occur either with light or with heat. And so those are going to be my two conditions that I can change. And the light could be just any old light. It doesn't have to be like ultraviolet light. If I was to, let's say I was to take pentane and add some bromine to it, bromine is an orange liquid. If I added that to the alkane, it would not change color immediately because it would take a while for the bromine to react. If I held it up like to the sunlight, which means I'd have to do that in like May or June around here now, it would change slowly. If I had an overhead projector, one of the old overhead projectors, if I put it on that, a real intense light will also change it. So it doesn't have to be ultraviolet light, it just has to be a fairly strong light if we want the reaction to go quickly. And heat, we'll talk about heat Friday. That's probably going to be greater than 300 degrees Celsius. So here's the overall reaction. So what we first want to talk about is the mechanism. It's a 6-step mechanism. And all free radical reactions start with what's called the initiation step. So the initiation starts the process. And what happens is that your halogen, I'll do this with Br2, in the presence of the light or the heat, the bromine molecule will break apart into two bromine atoms. And the way we show that is by using fishhook arrows that indicate the movement of one electron. So I'm going to break the bromine-bromine bond, and I'm going to give each bromine a dot, an electron. There will be no charges in this reaction because all of these are what are called homolytic bond cleavage. There's no great electron density or electronegativity difference. So there's no reason why one bromine should get 2 and the other bromine should get 1. They have equal strength, or not, they have equal strength. What's the transition state of this reaction look like? Partial bond between the bromines. No charges. And then 2 bromine atoms. And if we put the lone pairs around the bromine, you would just see that, oh, well, that's nothing more than just 2 bromine atoms. When the unpaired electron is on a carbon, that's when we'll call it a radical. But I sometimes will call it a bromine radical. I mean, it's truly a bromine atom, but it's got an unpaired electron. So that's the initiation step. And the thing is, I don't have to break apart all the bromine. I just have to break apart a couple of them. Because the next series of steps is what's called the propagation. So in the propagation step, what's going to happen is a bromine atom is going to react with a methane molecule, and it's going to abstract a hydrogen from the carbon. And the arrows will look like that. So the carbon-hydrogen bond will break. The H dot will combine with the Br dot. And then the carbon will be left with an unpaired electron. So in terms of the transition state of this step, we're going to have a partial bond from the bromine to the hydrogen, partial bond from the hydrogen to the carbon, and that's it. Again, no charges, no partial charges because there's no charges. Josh?
The arrow that's going from the CH bond in towards where the plus is, does that go into the space or does that go onto the hydrogen?
That's used to pair up with the hydrogen's dot that it's forming by breaking the bond. So if we look in the transition state, this is the bond that's forming while that's bond's breaking. So if we thought about breaking the CH bond first into an H dot and a C dot, that H dot would then combine with the Br dot to make the HBr bond. Okay, so that's propagation step 1. My bromine atom generated a radical, and this is the radical. The carbon with the unpaired electron. So then that newly formed radical is really unstable, and so now it's going to react with a molecule of bromine and a molecule of intact bromine. Now you might say, but didn't all the bromine break apart into Br dots? No. Because I think I said just a minute or two ago that you only need a small fraction of the bromines to break apart. So what's going to happen here is if you think about breaking the bromine-bromine bond, then the Br dot is going to pair up with the CH3 dot. And my transition state is going to have a partial bond between the carbon and the bromine, and between the bromine and the bromine. So the bond that's forming and the bond that's breaking, and then we're going to end up with our product, CH3Br, and we're going to end up with another Br dot. That would be one phrase to use, is that it's kind of a cascade reaction. But we call propagation. So one radical leads to the production of another one. So that's why we don't have to break all the bromine apart in the initiation step. We just need a few molecules. Because every time one of those reacts, it generates another one. So those are the two propagation steps. One radical propagates another, which is what the term is. All right, so everybody with me? So when does this end?
Does it end when there's no more light?
Well, it could be. It's most likely going to end when there's no more reactants of any kind. So when you run out of stuff, the reaction's over. But again, this is the problem with radicals. All it takes is one, and it just starts this process. So we'll talk a little bit more about this, but I think it was just, Monday, that there was this issue with we have to breathe or we die, but when we breathe in oxygen, it's got a diradical form. And so that does the same thing. Every time it reacts, it generates another radical. And we don't have any alternatives. We can't just not breathe. So we'll talk more about that and how the process could be controlled in, let's say, a biological system. But short of running out of stuff, we have three ways to stop the reaction, which are called termination steps. So if you think about terminating this process, what would terminate it is to have two species with a dot come together and form a single bond. And since I have two species with a dot, A and B, that means two A's or two B's or an A and a B. Okay, so these are the last three reactions. The first thing that could happen is two Br dots could come together, each of them sharing the unpaired electron, going through the exact same transition state. Because whether I'm forming or breaking the bond, it's the same transition state. To then give me a Br2. So that's one termination step. Second termination step would be, let's react a Br with the CH3. Again, each one of those donating the unpaired electron to form the single bond. We're now forming a bromine carbon bond in our transition state on to form a molecule of the product. Now, don't get the impression that this is the way that a majority of this product is formed, because it's not. In order for two radicals to be in close proximity to react with one another, that means they'd have to not be next to something else they could react with. So a small amount of product might come from this coupling, from this termination step. The final is, so that's two A's and an A and a B. Now let's react two B radicals together. So let's react two methyls. They're going to each donate an electron. I'm going to form a partial bond between the two carbons. And now I'm going to get a new molecule called ethane. And so one of the things we look for in this reaction is, if this is really the mechanism, I should see some ethane formed in the product. And the other piece of terminology that we use is that whenever two carbon radicals come together, that's called a coupling reaction. So coupling's when you get two of the free radicals to come together.
So the two PRs coming together is a coupling reaction.
I use the word coupling to indicate any two unpaired, but truly it's supposed to be used with two alkyl radicals. So I mean, we had Wirtz coupling back with the Grignard, and that was when we took basically the alkyl group that was attached to bromine and the alkyl group that was changed into the Grignard and brought them together. The fact that that's called Wirtz coupling indicates that reaction is a free radical one. We didn't talk about it because it's really complicated, but it is most likely a free radical reaction. So there's a couple terms. This term is called, the abstraction of the hydrogen. So there's the 6-step mechanism that you can do with anything. All I have to do is give you an alkane, halogen, and I have to tell you which hydrogen you want to substitute. And then basically it's like taking this mechanism and erasing it to show the right carbon and the right hydrogen that's reacting. So I won't make that a take-home quiz for Friday, but I reserve the right to do that for Monday. And unless I forget, I probably will. So that means nobody will try and remind me. But don't worry, I'll probably remember anyway. So this is the step. So is everybody kind of okay with that? Because now we're going to move on to the really good stuff. Let's do some real reactions on better molecules than methane. So we won't take a big jump, we'll just go to propane. So here's my first question. How many unique products should I see as part of this reaction, as a product of this reaction? Two? Kevin? Three? What was your number? Well, you don't know if it's wrong until you say it. Wrong. So far I've got a 1, a 2, a 3, a 6. I mean, we can go up to 8 because there's 8 hydrogens in propane. Still wrong. All right. So what we do is, if we don't know, let's substitute each hydrogen with a bromine and name it. If we get a different name, we get a different product. So how about any of these CH3 hydrogens is going to form what? One bromopropane. So those 3 are going to give the same product. How about the 3 on this side? Same thing. So that means that there are 6 hydrogens that are going to yield 1 bromopropane. And I'm going to label those A. And I'm going to label this product A. So any of those 6 hydrogens being replaced by a bromine will give me the same product. How about, bless you, how about this CH2? Is that going to give me a new product? Yes. So both of them, substituting for either one, give me the same product, right? Okay, so there's a B. And there's product B. And only 2 hydrogens will give me product B. Substitution of 2 hydrogens will give me product B. So the answer is 2. There's 2 unique products of this reaction.
What about the other Br radical?
That's going to form an HBr. So the other product with both of these reactions is going to be HBr. And I don't care about the HBr. I only care about the alkyl group. Kevin?
So what are the relations between 2 of the propanes combined?
They could, but what are the likelihood of 2 propane radicals finding each other in the mixture? It's pretty low, so we're only going to focus on what's called the monosubstituted products. And I didn't mention this earlier, so I might as well mention it now. If I was to take something like pentane, react it with, put bromine in it, put it in the sunlight, and then take the products and analyze it by like GC mass spec, I would see all 5 products, or all 3 products, 1, 2, and 3 bromopropanes, bromopentanes. But then I would also see dibromos and maybe tribromos. We're going to specifically limit ourselves to just the monobrominated products or monochlorinated products. But that's not real life. Real life, we would see all of them. Okay. I've got a sense of deja vu. I have that quite a bit. You should have that quite a bit too. Where have we done this before? Particularly those of you that were in like my lab section. In NMR. Lab, easy answer, NMR, more specific answer. This is a way that you can determine how many different peaks, and I should say sets of peaks, that you should see in a proton NMR spectrum. If you replace that hydrogen with a bromine and you get a different name, it's going to have a different chemical shift. So this is a way we can say, oh, propane should have 2 sets of peaks in the NMR. So again, when we talk about that in NMR, I have to usually remind people of that's what we did in free radical halogenation. But since we didn't do free radical halogenation last semester, now it kind of all fits together. So, somebody be psychic and tell me what my next question should be.
Which is the major product?
Exactly. I got a reaction with 2 products. Which one's the major product? Now, this morning I asked that question, which one's the major product, intending it to be a rhetorical question, which means I would answer it. But then somebody jumped in and decided to answer it for me. Anybody want to do that this afternoon? It's okay. I'm not going to make fun of you. Well, I guess I did earlier. So that could happen. Josh?
Would the the 1 bromo propane be the major product due to the fact that the electron density around the methyl group is going to be a lot larger in surface area, essentially, than the 2 hydrogens in the middle? There's a more likelihood that the bromine radical is going to end up being one of those than it is.
Okay, I like that answer a little bit better. That there's more likelihood that the Br dot is going to encounter a CH3 than it would a CH2. I like that answer. That's a statistical thing, right? If I'm pure statistics, I am 3 times more likely to form 1 bromopropane than 2. Because it's 6 to 2. So purely based on statistics, I would predict to get a 3 to 1 ratio of those 2 products. If that's all the reaction is based on, is pure statistics. Now I'm kind of giving away the fact that that may not be all that the reaction's based on. But that's one way to look at this, is to say A is going to be the major product because there's more hydrogens. And that's a perfectly acceptable way to look at this. Now my answer would be, if you said which one's the major product, I would answer with, it depends. And then you would say, on what? Well, on Friday we're going to find out that whether I use light at room temperature or whether I use heat at 300 degrees Celsius. But in order for me to say it depends, I need another argument. And that argument probably should favor B. So here's my argument. What kind of radical did product A come from? Primary, secondary, or tertiary? It came from a primary CH2 radical. What kind of radical did product B come from? A secondary CH radical. Which one of those 2 radicals is more stable? Secondary. You might say, well, wait, you didn't go over that. Okay, same rules as carbocations, except a little bit more forgiving. Because a carbocation only had 6 valence electrons. If it was primary if it was primary without any help from the alkyl groups, 6 trying to get to 8 is too much. So what does that mean? That means no primary carbocations. And if you write primary carbocations, then I put an X through them and I say, oh no, a primary carbocation, and then no with anywhere from 1 to 4 exclamation points after it. I saw a number of those on the exam. Maybe on Friday I'll also, if I can remember in my mind what the common mistakes were, I will go over those so that we don't make those again. But primary carbocations are strictly forbidden except in mass spectrometry because it's a high energy environment. Primary radicals, 7 to 8, that's 7 electrons trying to become 8, that's not too bad. So you can get a primary radical at room temperature, it's just not very stable. So secondaries are still more stable. So the secondary radical is more stable. How many reactions have we done this year where the major product has come from the more stable intermediate? I mean, more than one would be a sufficient answer, right? So I could argue that product B is the major product because it is coming from the more stable intermediate. But again, what's my answer to what's the major product? It depends. So now we have to think about, and we did this a little bit last semester because Top Hat included the sort of energy diagrams that kind of crossed over. But I don't even know why I'm saying that because that was a long time ago. I can barely remember it. But in order for us to fully explain, okay, which one am I going to get under low energy conditions? Which one am I going to get under high energy conditions? I need to remember two things. And we will revisit these. Hammond's postulate and the Arrhenius equation. And in particular, the Arrhenius equation has the temperature in it and the rate of the reaction, so we can explain why raising the temperature might affect the relative rates of the reaction. But of course, Hammond's postulate is what gets us to Arrhenius equation. Okay. And actually, if you were to go back and look at the first exam from last fall semester, this is kind of the question that I asked, albeit way too early in the year, where you had to make that rationalization. Only it was with the carbocation and not with a radical. So we have this problem with it depends. So we need to talk about what the barriers or what the rate determining step is, which is the formation of these radicals. We need to talk about the Hammond's postulate and how the activation energy can become higher or lower. We need to talk about birds flying over mountains. Birds with low energy can only make it over certain heights of mountains or they crash into them and die. Same thing would be true for the hiker, analogy that I've used before. Supersonic birds with lots of energy can fly over anything, right? So that's how we're going to explain this radical reaction. But I can actually put some numbers to this so that we can actually calculate the ratios of these reactions theoretically. And so that's what we need to do that's what we'll do on Friday. And then when I give you a reaction, you'll be able to calculate very quickly, okay, this is the major product, this is not the major product.